Okay, so day 2 of graphing sine and cosine functions, and today we're going to apply some transformations. So in the last exercise that you guys did, I asked you guys to compare the sine and cosine parent function and identify some similarities and differences. So let's briefly go over those now that I place both of these functions on the same graph. Sine, a difference that you might have observed is that sine starts at 0, 0, that's the y-intercept, right? So sine is in pink here, and then cosine has a y-intercept of 0, 1. That's a difference. But they have a lot in similarity, right? They have a lot in common. They're both waves, and they both have a domain of negative infinity to infinity. They both have a range of negative 1 to 1. And really, if we compare the two graphs, they're really basically the same wave, except shifted over. So if I take the sine graph, the pink, and I shift it over to the left pi over 2 units, I would get the cosine graph. And similarly, if I take the cosine graph and I shift it pi over 2 units to the right, I would have the sine graph, right? And so notice that the cosine graph is just a horizontal translation of the sine graph with a 90-degree shift, or pi over 2 radian shift. So we call them complementary functions. And this is what the co in cosine means. Cosine is just the complementary function of sine. And additionally, because they both contain the word sine and cosine both contain the word sine, they make up the two functions that are also known as sinusoids. And that's what we're going to be graphing in this unit. They're just functions that is a result from transforming the sine function, the parent sine function. That's all. So the other thing that I had you guys do for your exercise in the previous section is identify transformations. So let's review some transformations that you might be familiar with. And it's all really the same thing that we've been doing with parent functions in the past, right? Remember, everything applied to the x is going to be in parentheses. Since it's my parent function is y equals the sine of x. Okay, everything applied to the x is also in the sine, and then everything outside of that is applied to the y. So the a value, you might figure it out by graphing it on Desmos and checking your answers from the previous exercise, but the a value is applied to the y, since it's not in the parentheses that we're taking the sine of, right? A is applied to the y, and it's being multiplied. So if I multiply the y coordinates of every point on that graph by a number, it's either going to stretch it vertically or compress it vertically. Okay, and then if a is negative, if I make the y value negative, it's going to be a reflection over the x-axis. So if it's a negative y, negative a, that's going to be a reflection over the x-axis. Okay, and if the absolute value of a is greater than 1, and I put absolute value because the negative is not part of the stretching. If a is bigger than 1, it's a vertical stretch. And if a is, the absolute value of a is between 0 and 1, if it's a fraction between 0 and 1, then it's a vertical compression. So I'm taking my wave and I'm stretching it vertically or compressing it vertically. And then what does the b do? Well, we're multiplying again. So b, we're multiplying, except here it's inside the sine and cosine, so it's going to be applied to the x. So when we multiply all the x coordinates of my function by a number, now we're stretching it or compressing it horizontally. Okay, and then again, if b is negative, then now it's going to be a reflection over the y-axis. But we don't have to worry about that too much. We're not going to be doing that too much. So if the absolute value of b is greater than 1, then this is going to be a horizontal compression. Remember, we said what's applied to the x is always opposites. So if I multiply dx by 2 is really a horizontal compression by 1/2. And if the absolute value of b is a fraction between 0 and 1, then it's going to be a horizontal stretch. Okay, again, everything applied to the x's opposites. So if I multiply the x by 1/3, then it's really a horizontal stretch of 3. Okay, and then all my adding, subtracting for transformations are my shifts, right? Vertical shift and horizontal shift. So for my h, because it's in the sine and cosine being applied to the x, that's left and right, that's my horizontal. So h is going to be the horizontal translation or shift to the left or to the right. Now for sinusoidal functions, the horizontal shifts we are actually call a phase shift. So just another term for sine cosine graphs. And then the k is outside those parentheses, so it's applied to my y, that's going to be my up and down, right? And those are my vertical shifts. No special term for it. Vertical shifts are vertical shifts and horizontal shifts are phase shifts. Remember, everything applied to the x is opposite. So if it's x plus 3, you're actually going to the left 3. If it's x minus 5, you're going to the right 5. All right. So let's look at something called an amplitude of a sinusoidal function. And all that is when you have a sine wave, when you have a function that is a sine wave, the amplitude is half the distance between the maximum y value and the minimum y value. Basically, half the distance between your high point and your low point, or really half the height of your wave. So if you got your wave, this midline, which we call the wave axis, which is really, think of it as like the middle of the road, okay, is right in the middle, and then the distance from this wave axis, this midline, to the highest point is the amplitude, and that is the same as the distance from this midline to the lowest point. That's the amplitude. And so you can see that this is the amplitude and this is the amplitude. The period that's in the diagram we're going to talk about in the next video, so you don't have to worry about that for now. And in the equation, the amplitude is just the absolute value of A, or basically just A, because your vertical stretch. Because the negative, remember, is just a reflection, so that doesn't really affect whether it's the stretching or the shrinking. So amplitude is just your vertical stretch. It's the distance from the middle of your wave, the wave axis, to the highest point, and also the distance from the wave axis to your lowest point. So let's do some practice on identifying the amplitude of different graphs. Okay, so I want you guys to do this for practice. I'm going to go through one example, and then I want you guys to pause the video and try another on your own, and then you can come back and watch to see if you got it. And then if you got it, then you can just skip on to the next one and do them on your own if you feel like you're good. Okay, so the amplitude in each of the sinusoidal functions, we're going to start by drawing in that wave axis, that middle of the road line. I'm going to pick something that's easier to see. Here it is. I don't know, maybe green. Here it is. Okay, here is the middle of the wave axis, the middle of the road, and the distance from here to the highest point and the lowest point is the amplitude. So this is the amplitude, this is the amplitude. We got an amplitude of 1 for the sine of x parent function. And then for my second function, you can go ahead and pause. You can look at it from the graph or from the equation, right? If this is my wave axis, the distance from this axis to the highest point is 2. The distance from this axis to the lowest point is also 2. So my amplitude is 2. And you can see that right from the equation as well. 1 sine x and 2 sine x. Okay, and in this case, for C, amplitude is also 1. Okay, and the only difference here is that I have a vertical shift up 1. So my entire graph got slide up 1, and so my wave axis is no longer on the positive x-axis. It's now at 1. So this is now the middle of the road, but the amplitude is the same. 1 unit from the middle to the high point and 1 unit from the middle to the low point. And then the last practice set is to ask you to graph. So given the equation, can you guys graph and identify the amplitude? So from the equation, it might be pretty easy to tell already that the amplitude is just 1/2, right? Right here. My vertical compression of 1/2. The amplitude is always just a number in front of the sign. Not the negative, but whatever the value is in front of that sign. But how do I graph it? It might be helpful to sketch out the parent function, just to, and it's good practice too, so you're familiar with graphing the sine function. If I want to sketch out the parent function, I have the sine of 0 radians is 0, and then the sine of pi over 2 is 1. And if you need the unit circle to help you figure it out, you can certainly draw it here, right? Pi over 2 is here is 1. The sine of pi, the y coordinate, remember, sine is y, is 0. And then sine of 3 pi over 2 is at -1. And sine of 2 pi is back at 0. And then I can go the other way. So just a sketch. I messed up there. 0, 1, 0. Okay, there we go. Alright, so that is my parent function, and all I'm doing here is vertically stretching by a scale factor of 1/2. So I'm multiplying all my y values. It's applied to the y because it's not in the sign. Multiplying all my y values of my points by 1/2. So if I'm stretching, well, 0, 0, that's going to stay at 0, 0, right? But pi over 2, 1 is now going to be at 1/2, and then 0, and then pi 0 is going to stay. All the x-intercepts are going to stay, and 3 pi over 2, -1 is going to be at -1/2, and then 2 pi 0 is going to stay. And so I'm just compressing my graph by 1/2. And all of my points on the wave axis, it's going to stay. And so I have a flatter wave. And that is y equals 1/2 sine x. So go ahead and pause and see if you can do the next one on your own. Okay, looking at my equation, my amplitude is 3. Remember that negative is not part of the vertical stretch. It is just a reflection over the x-axis. Okay, and because there are no shifts, my parent sine function is sine of x, and my wave axis is on the positive x-axis, is on the x-axis. And so all I'm doing here is I'm multiplying all my y values by 3 and then reflecting it over the x-axis, basically multiplying by -3, right? All my y coordinates. So 0, 0 again is going to stay the same because 0 times -3 is going to be at 0. And then this point, which was at 1, is now going to be stretched up to 3. but reflected over the x-axis, so that would be now at -3. Okay, and then all of the points on the wave axis stays. 3 pi over 2 -1 is going to be stretched down to -3 and then reflected over the x-axis, so now it'll be at +3. And then 2 pi 0 again stays. Okay, and then when I go to the left in the negative side, I have -pi over 2, -1, stretched to -3, reflect over the x-axis, now it's at 3. And then -pi 0 stays, -3 pi over 2 is at 1, stretched to 3, and then reflected over the x-axis, down to -3. Okay, and then -2 pi 0 stays. So I just have a vertically stretched wave. And remember, I'm just sketching here. These curves do not have to be perfect. As long as you just go through these points and just make sure that it is still a function. And that looks good.